In this video, we're going to learn about interpreting definite integrals of velocity and speed functions. So we're going to let v of t be the velocity function for a point that is moving on a number line. And what I want to note is that we already know that the velocity is the first derivative of the position function, or in other words, the position function is an antiderivative of the velocity function. And because of this fact, when we look at the definite integral from a to b of the velocity function, the fundamental theorem of calculus tells us that this is going to be p of t evaluated between t is equal to a and b. In other words, p of b minus p of a. And what it is I want to figure out what this actually means in the context of movement along a number line. So let me get a number line up. So let's just draw a line. And I want a nice big line because I don't want this to get cramped. And it does need to be a number line, which means I do need a 0 and I do need a 1. I'm not going to bother doing all of the points, but this establishes the scale. And since my definite integral is going from a to b, I essentially need to know where my point is at t is equal to a. And I'm going to just draw it somewhere over here. So this is where the point is at t is equal to a. So location of point when when t is equal to a. So that means the coordinates of this would be p of a. And now the point might wander back and forth, and I don't know where it goes. But you can see how if you look carefully, you can see how my cursor is going back and forth, and that comes all the way back here, and that comes here, and this would be p of b. Now, if I think about what this actually is, it represents the distance from this point out to that point. And that is hardly the distance that we actually traveled. No, what this turns out to be is it is the displacement of the point from t is equal to a to t is equal to b. I like to think about displacement as the net change in position. And what I want to mean by that is as follows in this particular kind of an example. If this definite integral turns out to be positive 3, that means p of b is 3 units to the right of p of a. In other words, if this was 2, this would be 5. On the other hand, if the definite integral winds up being less than 0, then that basically is saying that my displacement is going to the left. In other words, p of b is to the left of where p of a was. And so the integral of velocity just represents displacement, and that's because velocity itself represents which direction you are going as well as how fast you are going. And basically on this kind of a number line, when the velocity is positive, we are moving towards the right, and when the velocity is negative, we are moving with velocity is less than 0, we are moving to the left. And so displacement turns out to be what the integral of velocity is. Well, that begs the question. If we want to calculate the total distance traveled, how do we do it? And I kind of want to think about that logically, and then we're going to kind of put the symbols back in. So again, let me get a number line up here. So there's my 0 and there's my 1. And I want to kind of draw the motion of the point in two different colors. So we're going to have the point start over here at P of A. So this is where we are when t is equal to A. And in this yellow color, I'm going to think about when the point is moving that away. And at this point, I'm going to stop and turn around, and I'm going to actually call this C1. So this would be P of C1. T is equal to C1. And now what I'm going to do is I'm going to turn around, and I'm going to go back the other way. And this is going to become C2, or rather P of C2, because this is where I'm at when the time is equal to C2. And we'll turn around again and come back to here, and this is going to be T is equal to B. So this is P of B. And just to remind you, this direction here, P of B minus P of A, which is the integral from A to B of my velocity function, is the displacement. But now, what I want to notice is how would I get the total distance from just this little graph? Well, the total distance would be the distance between time is equal to A and all the way out here to C1. And I'm going in the correct direction, so I would be integrating the positive velocity function. And then I turn around. And so I'm wanting to think about what am I going to integrate from C1 to C2? Well, from C1, I'm starting over here, and I want to do this back in the red color. I'm starting over here, and I'm going this away. So if I integrate velocity, I'm going to get a negative number. So instead of integrating the velocity, I will integrate minus the velocity, which is the speed that I am going on that chunk. And that is then going to pick up the distance between these 2 points. And then finally, when I turn around, I'm going to wind up having the integral from C2 to B of the velocity function, which is positive again. And when I think about writing the integral these ways, this is going to give me the distance, the actual distance between P of A and P of C1. Then I want to look at the distance between P of C1 and P of C2. And finally, I add the distance between P of C2 and P of B. And when I do this, taking into account every time I turn around, we are clearly going to get the total distance. Now, it's also worth noting that on this chunk, V was positive, V was negative, and V was positive. And so when I stuck that minus sign in, what I really did is I said, I want to integrate the absolute value of the velocity. So in other words, what I want to make a note of is that the speed function is the absolute value of the velocity function. And if we integrate between A and B of the speed function, we are going to pick up the total distance. the total distance traveled. So if we need to do speed, we have to, rather, if we want the total distance, we have to find out every place where we turn around first.